In this module, I'm going to connect equations with graphs. The first element we talked about within a graph was its magnitude. There's really no equation associated with magnitude. A point on a graph, you would drop a line down to the horizontal axis, and that represents the point on the horizontal axis. Then you'd simply draw another line over to the vertical axis, and that would correspond to the magnitude at that point on the horizontal axis. Next, we talked about slopes. The slope is going to be the gradient of the tracing. The slope is going to be the change in the ordinate divided by the change in the abscissa, or the change in y divided by the change in x. Remember that we talked about when the slope was not constant, that there was two slopes that we could refer to. One would be the average slope, and the other would be the instantaneous slope. For the average slope, again, we are looking at the change in y divided by the change in x, or we would take the final y value minus the initial y value and divide that by the final x value minus the x initial value. And that will give us the slope from the final position to the initial position. If we are looking at the instantaneous slope, we can't look at the entire value. What we are going to do here is we are going to find the slope for 1 point above our point of interest and 1 point below our point of interest. So again, our slope is still our change in y divided by our change in x, but what we're going to do is we're going to take 1 point on either side of our point of interest, and we're going to find the slope between those 2 points. And again, we want to make that slope instantaneously small. Finally, let's look at the area under the curve. Remember, the area under the curve is the area between the tracing and the horizontal axis. Let's consider a case where the y value is constant. Therefore, it's going to be represented by a straight, flat line. In this case, the area under the curve is a rectangle. Recall that the area of a rectangle is equal to the height times the base, or the y value times the change in the x value, which in this case is going to be equal to the y value times the difference between the final x position and the initial x position. This is what happens if we have a constant value for the y. What if y doesn't have a constant value? What we're going to do in this case is we are going to take the area under the curve and we're going to break it up into several minute rectangular areas. And then what we're going to do is we are going to find the area of each of those small rectangles, and then we're going to sum them together. In this particular graph, you might not be able to see it so well, so let's just blow up a portion of the curve. Here you can see that we've made several small rectangles. Now the rectangles would actually be touching each other. I spread them apart here for a better visualization. What we're going to do is we're going to find the area under each rectangle by taking the y value and multiplying it by the change in the x value of that rectangle, and then we're going to sum them all together. Now you'll notice here that the area isn't represented completely by the area under the rectangle. Some portion of the rectangle is above the curve and some portion of the rectangle is below the curve. There are several ways in which we can increase the accuracy of the area under the curve, and we'll discuss those more in class. So that's how we connect the equations and the graphs.